This is Benjamin Dakota from the Maverick CFD team, and this is our project, the CFD analysis of a new nozzle discharge coefficient calculation method. First, we'll go over some basic explanations of what this project is about. Nozzles are fundamentally a tube section over which flow changes its velocity. These nozzles can take various shapes and are seen in several forms such as orifice plates, Venturi meters, and servo valves. Nozzles are important tools in controlling flow within a system. A rocket engine, for example, may use a nozzle to accelerate distinct liquids and gases to serve functions such as fuel injection, or the expulsion or repurposing of exhaust gases. Discharge coefficient refers to the ratio of the experimental mass flow rate at the exit of a nozzle to the theoretical mass flow rate. This ratio serves to account for all the losses the fluid experiences, be them thermal, due to perpendicular interactions, or otherwise. Therefore, for situations where accurate calculations can be critical in terms of safety, performance, finances, and more, a reliable method for prediction of this discharge coefficient is highly valuable. Currently, various ways to do this have been proposed, which vary depending on the type of nozzle being used, how it is manufactured, and more. All three of these constructions on screen utilize different equations. But usually, the fluid's characteristic property in use is the Reynolds number. Using this poses a dilemma, as the Reynolds number is based on the viscosity of the fluid, a property that is insignificant when dealing with inviscid flow such as airflow. We were tasked by our client, Dr. Robert Wood, to investigate the effectiveness of a new non-dimensional number based on pressures for discharge coefficient prediction, which would replace the need for the Reynolds number-based methods. This new number, N sub n, is a function of the upstream pressure P sub u and the downstream pressure P sub d. This method uses experimental data to create theoretical curves based on the maximum and minimum data points gathered and the adjustment coefficients to create the best possible fit. To acquire this experimental data, we use CFD software, specifically ANSYS Fluent. Computational fluid dynamics refers to a branch of fluid flow study that uses numerical analysis and data structures. The flows domain is divided into fine segments called nodes and elements over which fundamental fluid flow equations are solved, allowing for a complete knowledge base of the flow's behavior given a set of conditions. We should touch on the orifices we have been using for this project and what differentiates them from one another. The characteristic geometric parameter for each of them is beta, the throat to chamber diameter ratio. The theoretical mass flow rate equations are affected by the geometry of the orifice through beta and the throat's area, but all other variables, including this area, are held constant across all the three orifices. Here you can see the changes in the throat geometry as you change the beta of the orifice, going from beta equals 1/3, 1/5, and 1/8. During the first semester of the project, we were tasked with the validation of the results obtained in summer 2020 by the Fluidize team, and to verify the accuracy of the new non-dimensional number-based method to create a discharge coefficient curve. In short, our results were aligned very closely with the Fluidize team's findings. We obtained results that were on average only 3% off from theirs. And the results of our implementation of the new non-dimensional number method on average only had a minuscule 0.5% error with the experimental data. This semester, we were tasked with studying the effects of fluid medium changes on the method, since this method was intended to circumvent the use of viscosity-based Reynolds number. It was tested using air, so the efficacy of the method on the flow of more viscous fluids such as water has to be verified. Through the semester, we successfully ran simulations using liquid water as a fluid medium, exploring the same range of pressure used for our air simulations for all three nozzles. At first look, the trends of the experimental data followed the expected curve, and implementation of the new non-dimensional number method led to very low errors. But upon closer inspection, the range pressure difference used so far was deemed insufficient, as the experimental discharge coefficient curve seemed incomplete. The scope of pressure difference was therefore increased to cover much lower pressures, going from 25 pascals to 200 kilopascals. After gathering data all the way through this range, the experimental trends could be properly seen, but it also demonstrated the inadequacy of the new method in its current state, as big gaps began to show that could not be corrected through the coefficient manipulation process. Dr. Woods proposed the addition of a linear term controlled by a new coefficient m, which would compensate for this gap between the curves. After this simple change was applied to the water results, the resulting curve fits showed vastly higher accuracy for all three of the nozzles studied, with average errors between 0.5 and 0.6% and max errors ranging from 1.5 to 2%. Similar margins of error as the results gathered using air. We then verified how this change affected the envisaged scenario of using air as a fluid medium in the beta equals 1/5 nozzle. And while the difference was not as drastic for this case, we do see a small decrement in error. We proceeded to obtain results for the full range using air on all three nozzles, expanding upon our work from fall 2020. And the results were very positive, as the experimental and new theoretical trends have almost a 1-to-1 relation, very closely matching the way our water simulation results came out. Therefore, we conclude that the addition of the linear term is a positive change to the method, with accuracy increased overall in comparison to the original model. We also conclude that the new non-dimensional number method results are reliable in both viscous and inviscid fluid mediums, with very low errors between them and the experimental data, around 0.6 for both air and water. We believe that studying the effects of reaching compressibility by simulating post-max 0.3 scenarios of air and other gases is a sound course of action, and that research on methods to achieve maximum accuracy in the setup of the CFD software is necessary, given the trends sometimes exceed the discharge coefficient values of 1. We believe that modifying the mathematical methods used by the software so the initial and boundary conditions can be more properly represented will eliminate these issues. We would like to thank Dr. Robert Woods for all the help and advice that he provided to us during the semester.